Okay, so this is the second lecture on direct sum decompositions, and in this lecture we are going to discuss the concept of invariant direct sums. Invariant direct sums. Okay, in the previous lecture we had discussed about a very important decomposition of a vector space, a finite dimensional vector space, where we had used the concept of projection operators to do so. In this lecture as well, we will have the concept of projection operators. Our main goal in this lecture is to be decomposing a given vector space into T invariant subspaces. That is the main goal of this lecture. Okay. So what I'm trying to say is that suppose you have V to be a direct sum of these subspaces. So W1, W2 till Wk. We need to have this decomposition in such a way that each W1, or I should say each Wi, is T invariant for some given linear operator. So it's T invariant. And then what we do is that if it's T invariant, then we restrict the operator T to each of these Wi's. We denote that by saying it's Ti. Now obviously since Wi is T invariant, so it's also Ti invariant. But then what specifically happens, let's see. Suppose you choose an element from V. Okay, so alpha is an element from V, but that implies alpha can be necessarily written as alpha 1 plus alpha 2 and so on till alpha k, such that each alpha I is from Wi, right? Then what is the image of alpha under T? So T of alpha is T of alpha 1 plus T of alpha 2 and so on till T of alpha k, right? But each Wi is T invariant, right? So T of alpha I is necessarily in Wi. So if it's necessarily in Wi and we have denoted the restriction operator Ti, which is the restriction of T on Wi, so we can write each T alpha 1 as T1 alpha 1 plus T2 alpha 2 and so on till Tk alpha k. So which implies we have got a decomposition of a linear operator, right? So we have got some sort of a direct sum of linear operators. That is, T is sum of these linear operators T1, T2 till Tk. They are necessarily linear operators because they are restrictions of certain linear operators. So I guess it's clear, right? So with the help of invariant direct sums, we can consider or we can conclude the decomposition of a given linear operator. That is more important to observe. Okay, clear? Now one more obvious thing to observe from here is that, so suppose you have a similar decomposition. Okay, so let's say suppose V is a vector space. Let this be a finite dimensional vector space, no worries, such that V has a direct sum decomposition W1, W2 till Wk, where for some linear operator defined on V, for some T in LV, each Wi is T invariant. Each Wi is T invariant. Okay. Okay. Now suppose I choose a basis of each of these Wi. So let Bi be the ordered basis of Wi. So since V is the direct sum of these Wi, so we can consider the basis. So this implies B, which considered of the sequence, ordered sequence of each of these Bi's, I ranging from 1 to k, is an ordered basis. Is an ordered basis. of V. But then what is the matrix of T with respect to V? What is the matrix of T with respect to V? Then I guess it's pretty evident from here that since B is of this form, so it's B1, B2 till Bk, each Bi is from each Bi is from Wi, and each Wi is T invariant. So what we can do is that we can consider Ti to be the restriction of T over Bi. Then this matrix is necessarily a diagonal matrix where the diagonal entries are typically the matrix of T1 with respect to the basis B1, the matrix of T2 with respect to the basis T2, and so on the matrix of Tk with respect to the basis Bk. Right? Is it clear? So this is a block diagonal form. Moreover, so suppose we write this as say A1, A2 till AK. Now what is the dimension of each AI? So the dimension of AI, so AI is a Di cross Di matrix. These are pretty evident from the previous lectures. Right? So if AI is Di cross Di matrix, where Di is necessarily the number of elements in the basis Bi, right? So it's basically dimension of Wi. Is it clear? So this tells us that if we have a invariant direct sum, because this is an invariant direct, this is only what we call an invariant direct sum decomposition. That is, we have a direct sum decomposition where each of the components of the decomposition are invariant under certain linear operator. So if we have a invariant direct sum of a given vector space, then the matrix of the linear operator under which each of these components are invariant, that becomes a diagonal matrix, right? So if each of these components, that is each of the restricted operators, they presume a simple form, then the matrix of T, it attains a simple form as well, because it completely depends on the matrices of each of these restricted operators, right? Is it clear? So that actually helps us in studying linear operators. That is the goal of this lecture, to be very specific, or the lectures which will be continuing. Okay. So having certain discussions of this type, let us come to certain properties related to this lectures. Okay. So let us come to the first theorem. So in the previous lecture, if you recall, we had a very important decomposition of a linear operator in terms of projection operators, right? So we will use that in this case. What we will say is that if sorry, it's a very bad start of our theorem. Let V be a finite dimensional vector space, or let just simply start with V being a direct sum of subspaces. So let V be the direct sum of these subspaces. Okay, and T be a linear operator on V. Let there be K linear operators. This was the exact statement we had studied in the previous lecture. That is the direct sum decomposition part 1. So let there be K linear operators, which are given as E1, E2 till Ek, which satisfy the following conditions, right? Which satisfy the following conditions. So what were the conditions? Condition number 1, that each Ei is a projection operator. That is, Ei squared is equal to Ei for all I. I am not writing the range of this index I, because we know that it ranges from 1 to K. Number 2, Ei Ej is the zero operator for all I not equal to J. Number 3, we have that we can write the identity operator as the sum of each individual operators, right? This we have. And number 4, we have that the range of each of these operators Ei is simply Wi. That is, the range of Ei is equal to Wi, right? then we claim is that, or rather the statement of the theorem is that each of these Wi's are T invariant. Each Wi is T invariant if and only if T commutes with each EI. With each EI. That is, TEI is equals to EIT for all I. I ranges from 1 to 10. Right? Okay. I know such a decomposition exists. We had proved in the previous lecture that provided you have certain linear operators such that 1, 2, 3 condition holds, then you can consider these subspaces Wi's, which are range of each of these EI's, which is a direct sum decomposition of these. So necessarily such a decomposition specifically exists. Okay. We want to say that provided such a decomposition we have, with respect to each of these projection operators, then each of these Wi's are T invariant if and only if T commutes with each EI. Now, what is the claim? No, what is the purpose of this statement? So now we know that this part is trivial. That is trivial in the sense that such a decomposition exists provide for a certain vector space. So if we consider a linear operator which commutes with these EI's, then this vector space actually decomposes into invariant direct sum, invariant T invariant subspaces. That is, we have attained a invariant direct sum decomposition of the vector space, and that naturally has a very important consequence, because we consider we then get a diagonal form of the matrix representation of T with respect to the ordered basis, where the basis elements are from each of these each of the Wi's, right? Okay. So this you can think of one characterization of invariant direct sum decompositions. Okay, let's start with the proof of it. The proof is fairly simple. We need to show that Wi is T invariant, provided that T commutes with Pz. So let us start with that first. Okay. So suppose Wi is, suppose TEI equals to EIT for all i's. What we need to show is that to show that Wi is T invariant. Wi is nothing but the range of EI. Okay. So we need to consider an element from Wi. We need to show that the image of that element under T is inside W. So let alpha be an element from Wi. But that implies there exists. So now recall the following fact. We had that alpha is in the range of some projection operator E if and only if E of alpha is equals to alpha. Right? In the previous lecture we had discussed this fact. So that means EI of alpha is equal to alpha. But then what is T of EI alpha? Now, T of EI alpha is basically T of alpha. But T and EI commute, right? So this is basically, so EI T alpha is equal to T alpha. But this was an if and only if condition, right? So that necessarily means that T of alpha must be inside the range of EI, and the range of EI is nothing but Wi, right? So therefore Wi is T invariant, because if you choose an element from Wi, the image of that element from under T is still in Wi. Alpha was arbitrarily chosen, right? So T of the whole space, the image of the whole space Wi under T is contained in Wi, right? So the first part is, the necessary condition is obeyed. Let us prove this. But I think we have proved this only. No, we had proved the, yeah. We need to show this, that if W is T invariant, we assume that W is T invariant. To show Wi is T invariant, to show that T and EI commute. Okay. So let us start with this. Okay. Now we have this, that this is given in the theorem, that the identity operator can be written as the sum of these projection operators. Right? So I is equals to E1 plus E2 till ek, right? So that means if you have some alpha, then you can write this as E1 alpha plus E2 alpha. This was also one part of the theorem which we proved in the previous lecture, E2 alpha till Ek alpha. Because we had discussed that these operators are such that Ei of alpha is sent to alpha I, where alpha is the sum of these elements. So alpha I can be considered to be the ith component of this sum, right? So this statement is obvious. Then what is T of alpha? So T of alpha is basically, so it's T1 E1 of alpha plus T2 E2 of alpha, and so on till Tk Ek of alpha, right? Now Wi is T invariant. So if Wi is T invariant and each of these Ei alphas are from Wi's itself, right? Because Wi is the range of Ei. So we have Tej of alpha for some j is in Wj, right? Because Wj is T invariant. T invariant and Ej alpha is inside Wj. Wj is the range of Ej, right? By definition. And Wj is T invariant as we said. Okay. So what do we have from here? So then what is Ej T of alpha? So it's summation over I is equals to 1 to k Ej T Ei of alpha, right? Okay, one statement we missed. Sorry, I need to conclude one thing before that. So if T Ej E alpha is an element from Wj, Wj is the range of Ej, then obviously, so that implies there exists some vector B such that T of Ej alpha is Ej beta, right? Because Wj is the range of Ej, so it consists of all those elements which are images under Ej. Those elements come from the vector space V. So we consider a vector V whose image under Ej will be obviously contained in Wj. Since this is also contained in Wj, they must match at some point. So T of Ej alpha is equals to Ej beta for some vector V. For some vector B. Clear? We're going to use this statement. Okay. So let this be 1. Now, what is Ej of T alpha? We restart from here again. So it's basically Ej T1 E1 alpha plus Ej T2, not T1, Ej T E2 alpha, and so on till Ej T Ek alpha. Right? This is what we have. Right? Is it clear? Is it clear? But we have that T of Ej is Ej beta, right? So if I consider the compact notation, then it will be more visualized. So it's of the form Ej Tei, consider it as is in this form. So I ranges from 1 to k. But T of Ei alpha, we have alpha here, right? So T of Ei alpha, from here we can say it's Ei beta, right? So this is equal to summation I equals to 1 to k. So it's Ej Ei and beta I, let's say. Okay. Is it clear? Or it won't matter. It won't matter to be very specific. We can consider this to be, yeah, we can consider this to be beta only. I think it's, yeah, so this will do. But what is Ej of Ei? So Ej of Ei, we recall we have also given the fact that Ej is 0 for all I not equal to j and Ej squared is equal to Ej, obviously because it's a projection operator. So every term of this expression becomes 0 when I is not equal to j. The only which term remains? So it only the only Ej Bj terms remains. So only this terms remains, Ej beta. right? Right? Is it clear? Is it clear? Now, so from here, now from 1, we can write that this as T of Ej alpha, right? From 1, right? Therefore, what we conclude? We conclude that Ej T alpha is equal to T Ej of alpha for all alphas, right? For all alphas. Alpha was an element from Wj, I guess. Yeah, alpha was an element from Wj, correct? But that necessarily won't matter. No, alpha was an element from V. Sorry. For all vectors alpha was an element from V, right? So if these linear operators have the same image, that is EJT, this linear operator, and TEJ, this linear operator, have the same image over all the vectors alpha coming from the vector space V, then that necessarily implies that they are identical. TEJ, right? So they compute. Clear? Is it clear? I guess it's clear. Okay. So now we again want to introduce the concepts of diagonalizable operators in this lecture. Okay. So how do we do so? Obviously, it will have some important conclusions. Let us just start with it. So we consider diagonalizable operator. Okay. Consider diagonalizable operator. Consider a diagonalizable operator on a finite dimensional vector space V over F. Okay. Now let C1, C2 till Ck be its distinct eigenvalues. Be its distinct eigenvalues, and W1, W2 till Wk be the corresponding eigenspaces. Be the corresponding eigenspaces. Okay. We know that in such a case, V can be written as a direct sum decomposition of these eigenspaces, right? Of these eigenspaces, Wk. Is it clear? Now, obviously, if such a direct sum decomposition exists, then from the theorem we had in the previous lecture, then therefore there exist scale linear operators E1, E2 till Ek such that they obey these conditions, right? So Ei squared is equal to Ei, obviously for all I, so that for all I, then we have Ei Ej is equals to 0 for all I not equal to j. Number 3, we can decompose the identity operator under these operators, right? And we have the range of Ei to be the eigenspace Wi. We have this in hand, right? Okay. So now if I choose an element from V, let alpha be an element from V, then alpha can be necessarily written as alpha 1 plus alpha 2, so on till alpha k, such that alpha I comes from Wi. Then that means, what is T of alpha? So T of alpha is T of alpha 1 plus T of alpha 2 plus T of alpha k. But we had found the way we introduce this is that each of these alpha i's are from Wi's, right? Wi is the eigenspace of the eigenvalue Ci. That means Wi consists of the eigenvectors corresponding to Ci. So T of alpha 1, or rather I should say, so I can just write it in language, that since each alpha I comes from Wi, it's the eigenspace, sorry, it's the eigenvector of, or rather I should say corresponding or associated with, to Ci. Therefore, what is T of alpha 1? So it's C1 alpha 1, right? what is T of alpha 2? So it's C2 alpha 2, and so on till we have here Ck alpha k. Is it clear? Is it clear? Okay. Now, one more thing to obviously have in hand is that, so we have k linear operators E1, E2 till Ek such that the identity operator can be written as E1 alpha plus, sorry, E1 plus E2 and so on till Ek. Okay. So this necessarily implies us to write T of alpha as C1 E1 of alpha 1, sorry, yeah, so E1 of alpha, right, E1 of alpha plus C2 E2 of alpha and so on till Ck Ek of alpha. Or let us do it in this form. Let us do it in this form. So if I suppose, what is E1 of alpha? So recall that when we have such a decomposition and we have k linear operators such that whatever conditions we have that is there, then E1 of alpha necessarily has the image alpha 1, or Ei of alpha necessarily has the image alpha I, where alpha I is the ith component of the sum of alpha, right? Some representation of alpha, right? What we do is that if we have alpha in this form, okay, let me explain this statement I wrote. Now, since we have alpha in this form, alpha is equals to alpha 1 plus alpha 2 till alpha k, then from here we can say that alpha can be written as E1 of alpha plus E2 of alpha and so on till Ek of alpha, because I can be written like this. The identity operator can be written in this form. So from here, if I consider this image, then what is T of alpha? So T of alpha is T of E1 alpha plus T of E2 alpha and so on till T of Ek alpha. Now E1 alpha, E2 alpha, these are elements from Wi, or I should say each Ei alpha belongs to Wi, right? So if each Ei alpha belongs to Wi, so they are basically eigenvectors associated with the eigenvalue Ci. That's basically, so it's C1 E1 alpha plus C2 E2 alpha and so on till Ck Ek alpha. One more way of representing this is in this form, that we know that the eigenspaces are T invariant. Eigenspaces are T invariant. So we can write this as E1 T alpha plus E2 T alpha and so on till Ek T alpha, since eigenspaces are T invariant. Obviously here T is the linear operator we are discussing, but T of alpha is necessarily, so if I restrict this to, no, I think this won't work, right? Because we need to have the eigenspaces alpha 1. No, this won't work. This won't work. Sorry. This won't work. We can obviously commute these operators because of the fact that each eigenspaces are T invariant, but it's of no use in this case because alpha is chosen to be an arbitrary vector from V, right? We are not dealing with alpha 1s here. We were dealing with alpha 1s here, right? So yeah, so it will trivially follow from the fact that each Ei alpha is an element from Wi. So this is C1 E1 alpha plus C2 E2 alpha and so on till Ck Ek alpha, right? So therefore T can be decomposed in these linear operators. So T can be done as C1 E1 plus C2 E2 and so on till Ck Ek, right? Is it clear? Now if T can be done in this form, then what can be the form of T squared? So if you just have T squared here one more time, so this is the constant, so let me just write one step. So T square of alpha is T of T alpha, so it's T of C1 E1 alpha plus C2 E2 alpha and so on till Ck Ek alpha, but that's basically equal to C1 times T E1 alpha plus C2 times T E2 alpha and so on till Ck times T Ek alpha. But Te1 alpha is again C1 alpha, so it becomes C1 squared alpha. Here you have C2 squared alpha, and here you have Ck squared alpha. Clear? Okay. So therefore, inductively, T to the power R of alpha is nothing but C1 to the power R alpha plus C2 to the power R alpha, and so on till Ck to the power R alpha. Right? So if I have these powers of T written in this form, then I can consider any polynomial under T. Right? Therefore, for all polynomials G over F, Gt of alpha is nothing but G of C1 alpha plus G of C2 alpha, or we can write this directly in this form, right? Have I done a mistake here? Yeah, we are talking about T squared of alpha, right? Yeah, sorry. So it would be, yeah, it would be C1 square of E1 alpha. This is E2 alpha, and this is Ek alpha. Correct. So therefore we can write that, sorry, we can write that T to the power R can be decomposed as C1 to the power R E1 plus C2 to the power R E2, and so on till Ck to the power R Ek. Correct. This is the correct one. Right. So therefore, for all polynomials G over T, what is G of T can be decomposed as? So it can be decomposed as GC1 of E1 times E1, sorry, plus G of C2 E2, and so on till G of Ck Ek. This is just an observation that if I choose the Lagrange interpolant polynomial, that is, we choose Gx, which is necessarily written as Pjx, which is the product of these forms where I is not equal to j, x minus ci over ci minus cj. I guess cj minus ci. Yeah, it's cj minus ci to be specific. Then what is Pj of ci? So it's delta ij, right? Therefore, how can Pj of t be written? So it's Pj of C1 E1 plus Pj of C2 E2, and so on till Pj of Ck Ek, right? So we have a term Cj obviously in between, so Pj Cj will become 1, so we just have a Ej here, right? But what conclusions did we actually draw? We actually drew this very conclusion. Let me just write the theorem here. So we can summarize whatever we viewed just now as a theorem. The theorem is as follows. So let T be a linear operator defined on a finite dimensional vector space V over F if T is diagonalizable, and if C1, C2 till Ck are distinct eigenvalues of T, then there exists k linear operators which are necessarily given as E1, E2 till Ek, such that they obey these conditions on V, obviously, on V, such that they obey these conditions. That is, we can write the linear operator T as a linear combination of these operators, but the coefficients come from these distinct eigenvalues, right? So it's C1 E1 plus C2 E2, and so on till some Ck Ek, right? Number 2, we can decompose identity operator as E1 plus E2, and so on till so we have here Ek, right? Number 3, that each Ei is a projection operator. So Ei squared is equal to Ei for all I. Number 4, ei ej is equal to 0 for all I not equal to j. And number 5, which is again obvious, that the range of ei is w, right? Or we can say this to be the null space of T minus Ci of, right? So these are the observations we have in it. Our concern is to prove the converse of this. Okay, we are to prove the converse of this. So let me just write the statement. So conversely, if there exists k linear operators, k scalars, k distinct scalars, which are C1, C2 till Ck, and k non-zero linear operators E1, E2 till Ek, which satisfy the conditions. Satisfying the conditions 1, 2, 3. We need this. So we need to satisfy the conditions 1, 2, and 4. Okay, satisfying the conditions 1, 2, and 4. Then T is diagonalizable. Where each of these scalars C1 till Ck are the distinct eigenvalues of T, where C1, C2 till Ck are distinct eigenvalues of T, and the other conditions we have, that is 3 and 5, follows immediately. Okay, so we will prove this part in the next lecture, and after proving this part we will be then concerned about what we have as the one of the most important decomposition theorems of linear algebra, which is called the primary decomposition theorem. Okay, so meet you guys in the